In this video I would like to show how to easily do a loop transfer function measurement of a typical power supply. What you see right now is the setup of an LM26001 evaluation board from National Semiconductor. It's a step-down DC to DC regulator, and here you can see the input voltage supply, which is set to 12 volts right now, and down here you can see a resistive load, which is causing the power supply to provide about half an amp of output current. Now, the interesting parts about the loop transfer measurement is the little cable that I attached here to the board, which goes to a small 20 ohm resistor, which is in the feedback path of the power supply. And I have two scope probes set up to this to either side of this 20 ohm resistor, and then an injection transformer which injects a small signal into the loop. Now, the injection transformer is just a standard off-the-shelf transformer. It doesn't really matter which transformer is selected. The purpose of the transformer is just to have only AC coupling, and that the injected signal is that there's no DC fed into our loop that we want to measure. Now you can see the input of this injection transformer is going to a signal generator up here, and this signal generator right now is injecting a sine wave signal of about 27 kilohertz. And now, when looking at the scope probe of the two waveforms that I measure, we can see the voltage measurement on the top, channel 1, of one side of the injected signal, and as channel 2 on the bottom you see the waveform of the other side of the 20 ohm resistor where I injected the signal. And now, in order to draw a Bode plot, we can measure at different frequencies and just see how the gain changes and how much phase shift we have, because that's what a Bode plot shows. It shows the gain a signal sees when going through the loop, and the phase shift. And now, as I've shown, at 27 kilohertz I see two sine waves with a little bit different amplitudes. Here in the top, channel 1 shows a little bit larger amplitude, and now what we can do is we can change the frequency of the injected signal by changing the frequency on the signal generator, and we see, at lower frequencies, now I'm at 15 kilohertz, the one channel has much larger amplitude than the other channel. And now let's look at a typical spot at about 11 kilohertz on this particular power supply. We can see that the one channel is about 3 times the amplitude of the other channel. It's usually what you do in order to see the amplitudes is you go to cursors, and then you go to amplitude, and here now we can change our cursors around and see that the channel 2 down here has about 13 millivolts of amplitude, and looking at at channel 1, we see that it is about 3 times as much. So we have about 37 millivolts, 38 millivolts peak to peak on the other channel. And so we know the voltage factor of these two amplitudes are about a factor of 3, which yields about 10 dB of gain. So we know at 11 kilohertz, because up here our injected signal is 11 kilohertz, we have a 10 dB gain. And now it's also interesting is to see what the phase shift is, and that's easy to measure. We just change to time our cursor here, and we move the we need a reference point, which is, let's say, the peak here of channel 1. So we put our little arrow here, and then we look here on channel 2 to the peak of the sine wave, and there is some shift, and this shift is the phase shift. And it might not be so easy to see in the video, but from this peak to the peak here of the other channel, there's a phase shift of about 80 degrees. So we know 80 degrees at 11 kilohertz we have 80 degrees of phase shift. And the other really interesting point of such a Bode plot obviously is the 0 dB crossover. What does 0 dB in gain mean? 0 dB means that the signal amplitude of the injected signal is the same as the signal amplitude after the signal crossed or ran through the loop. We want to have this signal amplitude to be the same. Then we know, oh, the transfer function has not changed the gain, so it's a gain of 0 dB. And so I'm changing the frequency around on the signal generator until the amplitude of channel 1 is about the same as the amplitude on channel 2. And that is the case at frequencies of about 40 kilohertz. So now we can see both amplitudes are about the same, so my gain at 40 kilohertz, because I set my signal generator to 40 kilohertz, is the gain is 0. And in other words, we know at 40 kilohertz now our loop of this power supply has the 0 dB crossover. And now these measurements can be done at different frequency points. We can measure the gain, so the amplitude difference between one of the channels and the other channel, and we can measure the phase shift. And step by step we can plot a relatively accurate Bode plot. And this is mostly useful for people that don't have a network analyzer that sweeps the frequency automatically and measures both signals and does all the math work for you. So with only a signal generator and an oscilloscope, you can get a reasonably good Bode plot measurement.